I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss in irreducible polynomial in R of x. Definition: let f of x belongs to R of x and degree of f of x greater or equal 1. F of x is said to be irreducible polynomial over R if it cannot be expressed as a product of two polynomials g of x and r of h of x belongs to R of x such that 0 less than degree of g of x less than degree of f of x and 0 less than degree of h of x less than degree of f of x. Remark: if f of x is equal to g of x into h of x and if f of x belongs to R of x is irreducible, then degree of f of x is equal to 0 and degree of h of x is equal to 0. A polynomial of a positive degree which is not irreducible is said to be reducible. So third one, the polynomial x square plus 1 belongs to z of x is irreducible over z, but it is reducible over c as x square plus 1 belongs to c of x and x square plus 1 is equal to x plus 1 I into x minus I. Any polynomial of degree 1 over R is irreducible over R. The units in R and R of x are the same. Every irreducible polynomial in R of x is an irreducible element in R of x. Let f of x belongs to R of x be an irreducible element in R of x. We have to prove that f of x is an irreducible polynomial in R of x. Let it possible f of x is reducible over R. Therefore, f of x is equal to g of x into h of x, where g of x, h of x belongs to R of x, with 0 less than degree of g of x less than degree of f of x, 0 less than degree of h of x less than degree of f of x. As a degree of g of x greater than 0 and degree of h of x greater than 0, g of x and h of x are not constant polynomial and g of x, h of x does not belong to R, hence they are not unit in R. By lemma, f of x and g of x are not unit in R of x, hence f of x is not an irreducible polynomial element in R of x. Thus, f of x is not an irreducible polynomial. Therefore, f of x is not an irreducible polynomial. This shows that the irreducible polynomial element in R of x is an irreducible polynomial in R of x. Remark: converse of above theorem need not be true. That is, irreducible polynomial in R of x need not be irreducible element in R of x. Consider the polynomial 3x square plus 3 belongs to z of x. 3x square plus 3 is an irreducible polynomial in z of x, but 3x square plus 3 is equal to 3 into x square plus 1 is equal to product of two polynomial in z of x which are not non-units in z of x. Since the units in z of x are the units in z which are 1 and minus 1, then 3x square plus 1 is expressed as a product of two non-zero non-unit polynomial in z of x. Hence 3x square plus 3 is not an irreducible element in z of x. Primitive polynomial f of x belongs to R of x may be reducible or irreducible over R. Example given: f of x is equal to x square minus 3x plus 2 belongs to z of x is a primitive and reducible as x square minus 3x plus 2 is equal to x minus 2 x minus 1. But f of x equal to x square minus 2 belongs to z of x is a primitive and irreducible over z. Next theorem, let R be a unique factorization domain. F of x belongs to R of x. f of x is an irreducible polynomial in R of x if and only if either f is an irreducible element of R or f is an irreducible primitive polynomial in R of x. Proof only part. Let f of x belongs to R of x be an irreducible polynomial element in R of x. Let if f belongs to R, then f will be a constant polynomial and it will be an irreducible polynomial element in R. Hence, if f does not belong to R, we have to prove that f of x is irreducible over R and f of x is a primitive polynomial. Now we have to prove that f of x is irreducible over R. Let f of x be reducible over R. Let f of x equal to g of x into h of x. G of x, h of x belongs to R of x. As f of x is an irreducible polynomial in R of x, either g of x or h of x must be unit in R of x. As unit in R and R of x are the same, either g of x or h of x is a unit in R. Hence, degree of g of x is equal to 0 or degree of h of x is equal to 0. And hence, but in turn shows that f of x is irreducible polynomial in R of x. Let f of x is equal to c into f1 of x, where c is equal to constant of f of x and f1 of x is a primitive polynomial in R of x. As degree of f of x is equal to degree of f1 of x, we get degree of f1 of x greater or equal to 1, and hence f1 of x does not belong to R. Hence, f1 of x is not a unit in R of x and c is a unit in R. Hence, f of x is a primitive polynomial in R of x. Thus, if a non-constant polynomial f of x belongs to R of x is an irreducible polynomial element in R of x, then it is an irreducible primitive polynomial in R of x. Let f of x belongs to if part. Let f of x belongs to R of x. If f of x is an irreducible polynomial element in R of x, then f of x is an irreducible polynomial in R of x. Let f of x belongs to R of x be primitive polynomial, irreducible polynomial in R of x. Now we have to prove that f of x is an irreducible element in R of x. Let g of x equal to h b naught. Hence g of x belongs to R. Now c into f is equal to c into gs is equal to c of g into c of gs. F is primitive, therefore c of f is equal to unit in R. Hence g of x is unit in R of x. Thus f of x is equal to g of x into h of x, and therefore g of x is unit in R of x. Therefore, this is that f of x is an irreducible polynomial element in R of x.